Okay, so I'd already recorded the first half of this video and the first half of this exam, and when I went back to edit it, I was like, this shit kind of sucks. So now I'm trying to speed run the first 5 questions of this exam again, and hopefully this time I'll do a better job at explaining what I want to explain. Anyways, this is exam 1 of fall 2023. This is actually the exam I did when I took this course, and the average was like all the other exam ones in like the mid to high 70s. I believe the average for this was a 74 or a 75. So, anyways, let's just get right into it. All right. Question 1. Question 1 gives us a circuit and tells us to find the voltage Vx. Now that you've progressed a bit in the class, it's really easy to see questions like this and jump straight to something like, oh, I know how to do mesh analysis. I'm just going to do that, or I'm going to do Nodal. When in reality, these questions are so much easier, especially when you see a question 1, you know it's going to be easy. That's the standard for every exam. So what I'm going to do is just add resistors in series and parallel until I can simplify the circuit and just use Kirchhoff's law to find Vx. So the first step is noticing that this 20 ohm resistor and this 30 ohm resistor are in series. So that means we can add them together and make them into a 50 ohm resistor. And now we can see that we have two 50 ohm resistors in parallel. And here's a little fun fact. If you have two resistors of the same value in parallel, their parallel sum is always just going to be half of that value. You can go ahead and use the normal formula to prove that to yourself, but I'm just going to skip that for the interest of time. So now that we've done that, we know that the sum of these two resistors is 25, and our reference voltage for Vx is not going to change, because if this is Vx, this is also Vx, and once we add them to each other like this, let's see, this is also once again going to be Vx, but this time with a 25 ohm resistor. And now, completing the circuit, we can see that we have a super simple weak 1 circuit. So all we need to do now is Ohm's law. We have Vx equals IR. I is, I forgot 2 zeros over here, 100 milliamps. I is 100 milliamps. And R is just 25 ohms. Take note of the units for these questions, because that is sometimes how they try to trip you off and make you choose the wrong answer. In these super simple questions, they have to find some way to trick you, and it usually comes down to units. Anyways, once we multiply those two, that would just be 2.5 volts, which is our voltage of Vx. And our final answer is D. Moving on to the next question, we have a fairly complex looking circuit, and we're asked to find the equivalent resistance between ports A and B. That means that they just want us to simplify the circuit as much as we can until we reach something like this, where we just have one resistor between terminals A and B, and we're trying to find what this resistance is. So to do that, we just need to find which resistors are in series, which resistors are in parallel, and just add them to each other until we slowly simplify the circuit. People usually have quite a bit of trouble figuring out how to approach these problems, because sometimes it's kind of hard to visualize what's in series and what's in parallel. So in this question, what my first tip is to find the most obvious step you can start with. And in this question, it's going to be adding these two and these two in series. Just by looking at the circuit, you can instantly see that these two are in series. So I'm just going to draw over the circuit itself. So we have 4 and 8 in series, which is just going to give us 12 ohms. And on the other side, we have 40 and 8, which is going to give us 48. Let's redraw that. 48. Okay, so that was a step that I assume most of you can do. What I would also recommend is to redraw your circuit every time you make a simplification. So, when I'm on an iPad, I can easily just white out on the circuit itself and simplify it. But on an exam where you can't do that, I recommend redrawing your circuit from anew every single time. Because time, at least for me and everyone else I knew, was almost never the constraint for 2K1 exams. Okay, so because now that we have our simplified circuit, you can recognize that these two share the same nodes. So we have a 12 ohm and a 24 ohm resistor in parallel. And if your circuit was still in the previous configuration without the resistors added in series, you probably would not have been able to see that as easily. So I'm just going to go ahead and once again take my own advice and redraw my circuit now with that 12 and 24 ohm resistor added in parallel. So 12 in parallel with 24 is going to be 1 plus 2 over 24. That's just 1 over 12 and 1 over 24, which is equal to 8 ohms. So now we have 8 ohms over here, 16 ohms over here. And once again, we can see now that we've redrawn our circuit, there's a next step staring right at us, which is adding these two in series, which I'm just going to go ahead and do on the same circuit. So we had a 16 ohms and we had an 8 ohms, so adding them together we're going to have 20 ohms. And this, if you don't recognize it as a parallel circuit, I can just redraw it as something like this, which should be easier to tell. So we have 24 ohms, 48 ohms in parallel, which adding those two in parallel should give us, let's see, 1 over 2 over 24, 2 over 48, plus 1 over 48 equals 48 over 3, which is 16 ohms. And 16 should be our final answer. Alright, I am speeding through this. Alright, next question. Which is the correct KCL equation at node 2? So, I hope that at this point you are very familiar with KCL. If not, it's super simple. What KCL says is if we have a node, the sum of all the currents going in and going out are going to be 0. That means that what they're asking us to do is find node V2, and note that node V2 extends all the way over here. This is all technically node V2. So it says take node V2 and will prove to us, or set up an equation that says all the currents going in and all the currents going out equal to 0. So what I'm going to do is just make an arbitrary decision that all the currents going into V2 have negatives in front of them and all the currents coming out of V2 have positives in front of them. Take note that you could do the opposite thing, and the only thing that matters is for you to stay consistent with your assumption. As long as you do that, you just end up with the same final solution, and you should be able to find your answer in the answer key, in the answer choices. So what I'm going to start with is the super obvious ones. So these two current sources. So we have I1 going into V2. So like I said, I'm going to put a negative sign in front of those. And we have I2 coming out of V2. Remember that this entire top node is V2 because they're all connected to a wire. So all that comes out of here. And now we get to the slightly trickier ones. So over here, I can define an I3 and an I4. Once again, my definition of I3 and I4 is arbitrary. You could define both of these currents to be going in the other direction, but in the end, as long as you do the math right, you will get the correct answer anyways. So going off of that, all of that equals to 0, right? So now all we need to do is to find what I3 and I4 are in terms of the values that we already have. So in terms of V2, R1, R2, and R3. So I3, we can write as V2 over R3. This is just simple Ohm's law. So if this over top is V2 and it's grounded on the bottom, and this is R3, the current coming down through R3 is just going to be given V equals IR. I is going to be V2 over R3. And the same thing applies to the other one. Applies to I4, but instead with two resistors this time. So we have V2 over R2 plus R1. That's it. It's as simple as that. So rewriting this, we have negative I1 plus I2 plus V2 over R3 plus V2 over R2 plus R1 equals 0. And looking through the answers available to us, we can see that B matches our answer perfectly. Now, keep in mind that if you had done it the other way around, where you defined currents going in to be positive and currents coming out to be negative, you'd have I1 minus I2 minus V2 over R3 minus V2 over R2 plus R1 equals 0. See, this at first glance does not exist in the choices. And a lot of people just go ahead and straight up circle none of the above without thinking of the fact that, oh, there's a 0 on the right hand side, so I could technically multiply both sides by a negative 1 and it would still be the same statement. So keep that in mind. Make sure you actually consider the fact that there could be different definitions for the signs of what currents going in and currents coming out are. Anyways, yeah, the answer to this is B. Question 4 is kind of a strange question. They give you this huge circuit and ask you what the current I2 is. And at first glance, you might be super overwhelmed given all this information they've thrown at you, and I'm guessing that's their plan. But what you can do is first pinpoint where I2 is, which is over here, and see that, what's happening? You can pinpoint where I2 is, which is over here, and notice that you can just find I2 using KCL around point D, because you already know what current's going in and what current's going out. So that means, technically, the only part of this circuit you need to look at is this, right? The rest of it is irrelevant, and it's just there to trip you up. So, yeah, now we can just do KCL. So we have 3 amps going in, so just like last time, I'm going to do negative 3 plus 2 amps coming out plus I2 coming out, all being equal to 0, given KCL. And rearranging this tells us that I2 equals 1 amps, which is our final answer. It's so easy to get confused with these questions given how much information they give you, but all you need to do is just take a step back and look at what they're actually asking you and how you'd normally go about finding that. Question 4 is continued, and once again they give you the same complex circuit and ask you what this time V4A is. So this voltage across our current source. So this time, once again, just like the previous question, you need to realize that they're giving you extra information just to trip you off. And to find voltages, you can make the connection of, okay, they're asking about voltages, so we should use KVL. And if you look through the circuit, there's a pretty nice loop over here where I can use KVL in. So this time, the only part of our circuit that matters is this. And I've left that 5 amps over there because we actually need to do KCL to find one of the currents in the branches, which we'll do to begin with. So first step is to find the voltages across all of these components. And to find the voltages, we need to see what current's going through the resistors. So the first current is I3, which is defined for us, which is already given to us. So I3 is negative 1 amps. And given that it's negative 1 amps, that means that through V3, there's actually 1 amps going this way. So now it actually matches our polarity and makes our lives so much easier. So we know that V3 is just 1 times 10 equals 10 volts. And we need to do the same with this one. Let's call this V5. I don't know how many V's we have here, but yeah, let's call this V5. And to find V5, we need to find I4. So we can do a super quick KCL at node B. So we have 5 amps going out, 4 amps going in, and to make all of this, and to make the sum of all circuits going in and out equal to 0, we will need to have another amp going in. So we'll have 4 amps plus 1 amp going in and 5 amps coming out, creating essentially an equilibrium. Now that we know that, I think it's actually smarter to change the polarity of V5 to be like this, since our 1 amp isn't actually matching their definition of I4. And that means we can find V5 by doing this time 1 times 4 equals 4 volts. So we have V3, we have V4, and we're looking for V4A. I'm gonna redraw the circuit in a simpler manner so that we can do our KVL without being confused. So we have V4A, we have V3, and take note of the polarities, make sure that the polarities in this circuit matches our definitions over here. And we can do a clockwise, let's say, loop. So I'm gonna say every time the arrow enters the negative terminal, I'm gonna put a negative sign in front, and every time it enters the positive terminal, I'm gonna put a positive sign in front. Once again, this is all arbitrary. You can decide what signs you want to put in front of it. You just need to stay consistent with it. So that means that our equation for KVL is going to be negative V5 plus V3 minus V4A all equal to 0. So that means V4A is equal to V3, which was 10 volts, minus V5, which is 4 volts, giving us that V4A is actually just 6 volts. And that is our answer. Again, with these types of questions, like I said, the first thing that confuses a lot of people is the extra information they give you. And the other thing people make a lot of mistakes in is the signs of their definitions for voltages and currents. So just make sure you pay extra attention to your definitions of voltages and currents, and don't let their current definitions, like this I4 over here, confuse you. This I4 over here does nothing for us. I can just get rid of it and define 1 amps going and find my 1 amp going in the other direction and just solve using that. I don't need to do anything with I4. Yeah, and the answer is 6. Alright, question 6 says, given the measured voltages and currents shown below, which elements supply power in the circuit? So this ties back to that one thing you learned in the first week of class and never went back to, which is passive and active sign conventions. Now, what you need to know is, unless the question specifies that it's using active sign convention, you can always assume that you're using passive convention. Like, that's what we've been doing for all these other questions, and it's what we'll also use for this. Now, what passive sign convention is that if you have elements consuming power, the current will be going from the positive side to the negative side. That means there's a drop in potential across that, like, consumer. And if we have something producing power, no, there's an R there, there you go, producing power, the current is going to go from the negative side to the positive side. So there's an increase in potential as we go across it. So all we need to do, given this information, is go through this circuit and see which one of these will be consumers and which one of these will be producing power. So going through A, we have 800 milliamps going from the negative side to the positive side. So this one is producing power. Let's just say P for that. And we can follow this 800 milliamps back to here across B and see that for B is actually going from the positive to the negative side. So there's a drop in potential. So this is consuming powers. It's asking us which elements supply powers. That's what we're going to do. And for E, we can once again see that this 1.2 amps is going through the positive side, coming out of the negative side. So this one is also having a drop in potential across it. So it is consuming power, and same goes for C. And for D, from a first glance, you might say, oh, this is also going, if you follow the 2 amps back, this might also be going from the positive side to the negative side. But that's where Jason McKinney says, you fell into my trap, because he gave us negative 26 volts. So in reality, what this is 26 volts with the polarity the other way around. So that means we actually have 2 amps going from the negative side of D and coming out of the positive side of D, if it was mentioned as how we normally would mention it, as 26 volts instead of negative 26. So D is also producing power. So our answer will just be A and D. Question 7 says, what are the correct Thevenin voltage and resistance for the circuit shown below? Now, these questions, there's really 2 ways to do them. You could either do them the way of source transformations, or you could just calculate VThevenin and REQ like separately. Source transformations, I'm going to skip that because I think a lot of people are way more comfortable with that. So I'm just going to do it in terms of calculating VThevenin and REQ individually, which I also think is easier for this question. So what the concept of VThevenin is literally just if this was an open circuit, an open like path like it is right now, what would the potential difference between A and B be? So all we need to do to find the potential difference between AB is to do a KVL within this loop. And to do a KVL within this loop, the first thing we need to notice is that if this was an open circuit, the current going through this branch would be 0. So that would be the same as this resistance like straight up not being there, because V equals IR, and if I is 0, no matter what the value of R is, the voltage drop across our resistor will also be 0. So there's that. So now we have one voltage, which is 5 volts. And for the other voltage, all we need to do is, once again, Ohm's law, 250 milliamps times 20 ohms gives us, I think, what does that give us? 5 volts, right? Yeah. And to find the other one, all we need to do is look at this side of the circuit and find the voltage across this 20 ohm resistor. And that is, once again, just Ohm's law. So we have 250 milliamps times 20 ohms, which just gives us 5 volts. So now we have a plus minus in this polarity because our current is going this way, 5 volts over here. And if we're trying to find VThevenin within this loop, it's just VThevenin equals 5 plus 5, because these two 5 volt sources, or these two voltages are in the same polarity, and our VThevenin voltage is in the opposite polarity, so it will be on the other side of the equation, or it would have a minus sign in front of it if you wanted to equate all of it to 0. So our VThevenin is just 10 volts. So that's alluding to the answer being G without us even solving for REQ, but as usual, they have to include a none of the above to make your life much more difficult. So we'll also solve for REQ. So REQ in this circuit is insanely simple. When you're finding REQ, always remember the first step is turning off your independent sources. So this one turns off and this one turns off, and voltage sources you replace with short circuits, and current sources you replace with open circuits. So that simplifies the circuit to 5 ohm source, 5 ohm resistor over here, a B, a 20 ohm resistor, that is a very wonky resistor, and an open circuit over here. And this is literally just two resistors in series, which means that A and B just have 25 ohms across it, which confirms our answer of G. Okay, we're on to the workout problems for this question, which I thought were all pretty standard. So question 8 says, sure, blah, 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 determine the equivalent resistance RAB for the circuit. So as soon as they say equivalent resistance and you see that there is a dependent source in the circuit, your mind should instantly go to an IV test. And what we do for an IV test, if you do not recall, we put a source of known voltage or current across our circuit, and we see what the current or voltage across it will be to be able to use just like Ohm's law to find the resistance of the other side of the circuit. So the very first step of doing an IV test is turning off your dependent sources. This is a step I see people forget all the time, and it makes solving the question so much more difficult, and it just gives you a completely incorrect answer in the end. So you would have done all that work and wasted all that time all for nothing, and you would probably get minimal points for the question. So do not forget to turn off your dependent sources. Once we do that, it's the usual drill of voltage sources being replaced with short circuits and current sources being replaced with open circuits. So I'll go ahead and redraw our circuit over here. 12 ohms. And don't forget your definition of IX. So this is the circuit we have now. So the next step in an IV test is us, I forgot this part, is us deciding whether or not we want to put a voltage source or a current source as our test source. Now, for some questions, it's easier than others to realize what's going to be easier, but it's important to note that none of them are incorrect. For both of them, you get the same answer. It's just one might result in a couple more mathematical calculations that you might have to do. And there isn't really an easy way to tell which one's correct. And I hate saying this, but it's usually just intuition. There usually isn't an easy way to say which one's the correct one in quotations to use, but if you look a bit ahead into what your calculations are going to be, like for example, in this question, I think a current source is going to make my life so much easier, because as soon as I define this current, I can just do one KCL equation over here to find IX to use to find the voltage VT. So all you need to do is just think ahead with what you're going to be doing and how you're going to be calculating it, and that would hopefully make you realize that one source is easier than the other. Just like I said, it's not like the other one is wrong, it will just be a bit more difficult. So anyways, let's get into it. So yeah, I'll stick with my 1 amp source over here, and what we're trying to find is V-test so that we can use Ohm's law to find the resistance of the circuit. So what I'm going to do is, on this node, I'm going to do a KCL equation, which says I'm going to use a negative sign for anything going into my node. So negative 1 amp, negative 4IX, since these two are both going in, and positive IX for this current coming out of this side, all equal to 0. And if you rearrange this, you have IX equals negative 1 over 3 amps. So you can see how easy it was to find IX given that I put a current source over here. If I put a voltage source over here, I probably would have needed to use 2 equations and solve them simultaneously and all that, which I'd prefer not to do in an exam. So now that we have IX, all we need to do is find VT. And to do that, I think the easiest course of action is to do a KVL around this big loop. So given IX has a negative sign, we can define a current in the opposite direction of value 1 over 3 amps to get rid of the negative sign, and that would mean that we have a plus minus like this, 4 volts across this 12 ohm resistor. And for this other resistor, we just have the 1 amp going through it. So we have a plus minus 9 volts over here. So our KVL equation around the loop that I highlighted in blue will be negative VT. I'm just putting negative signs in front of everything that does not match the polarity of my loop, which I'm doing in a clockwise direction. So we have negative VT plus 9 volts minus 4 volts equals 0. And if you rearrange this, you should get VT equals 5 volts. So we have our I test was 1 amp, our V test is 5 volts, and given V test equals I test times Req, we have Req to be 5 ohms. Question 9 says, write a sufficient set of equations to solve for the mesh currents I1, I2, and I3 in the circuit below. And it says that we don't need to solve for the currents, and all we need to do is just write the equations in terms of this. So when it says sufficient number of currents, that means for the 3 unknowns we have, we need to write 3 equations. So we can start with I1, so I'll just name it mesh 1. And this one is actually super easy. We already know exactly what I1 is. Given that I1 is defined to be this current going over here, we see that it crosses a 2 amp current source. So it straight up means that I1 is defined by that source. So I1 is 2 amps. There we go. We are 1/3 of the way done. Now we can go ahead and do mesh 2. All right. Given we're going in a clockwise direction, I'm gonna define voltages where I enter the negative side as negative voltages, because I feel like that makes sense to me. And yeah, the other ones is positive voltages. So we start with a negative 10 volts, since we're going into the negative side. Then we have I'm actually going to ignore this definition of Vx because it doesn't really do anything for a loop, and I'm just going to define this as a positive voltage where we have 5 I2 minus I1. So we have I2 going this way, I1 going this way, and I'm just putting an arbitrary assumption that I2 is larger than I1 so that the voltage has a polarity of this way. And the nice thing about this is that as long as my signs are correct, it does not matter what my assumptions are. It will fix itself in the end. It might be that I1 ends up larger than I2, so we'll have a negative sign in front of it. And for the other one, I'm going to do the exact same thing, which is 20 I2 minus I3. And all of that equals 0. And then we can go do mesh 3. I'm going to use the same assumptions with my signage and all that. So I'm going to do 20 I3 minus I2. Once again, I'm just making an arbitrary decision that this is plus minus this way so that it just makes my life easier. And we have a negative 0.2 Vx, and we have a simple 15 I3, all equal to 0. Now this is almost what they want, except we have this pesky little Vx over here, and our equations need to be in terms of I1, I2, and I3 only. Now if we go back to the circuit, we can just see if we can find Vx in terms of I1 and I2. So Vx is defined with the positive side on the right and the negative side on the left. And if we look at the currents going through it, we have I1 going this way and I2 going this way. And for that signage to make sense, I1 needs to be larger. It needs to overpower I2. So that means that Vx can just be defined as 5 times I1 minus I2. And yeah, now we have a Vx that we can plug in over here and simplify our equations. I had to do a little cut there because the answer key to this question is wrong, and I was so confused why my answer wasn't matching. But it turns out that I am actually right. So all we need to do now is just simplify our equations and put them in the form that they want. So our first one is just I1 equals 2, which is already in the form they want, and the other ones are pretty easy to simplify. So all I'm going to do is expand this stuff out and rearrange them. So we have negative 10 plus 25 I2 and a negative 20 I3 minus 5 I1 equals 0, which would give us minus 5 I1 plus 25 I2 minus 20 I3 equals 10. So this is our second equation, and our third equation is also gonna be super simple to get to, which is just what we're gonna do is plug Vx into our equation and rearrange it. So we have 20 I3 minus I2, and that's gonna give us minus I1 minus I2. So that's just 5 times negative 0.2, which gives us negative 1. And let's not forget the plus 15 I3 equals 0. And rearranging this should give us negative I1 minus 19 I2 plus 35 I3 equals 0, which is our third equation. So these three would be enough for us to calculate the actual values of I1, I2, and I3, but since the question does not ask for them, we can just leave it in this form. Okay, question 10 is very similar to question 9, the previous question, where this time we're solving for the nodal voltages V1 and V2 using nodal analysis, and they just want us to simplify it into a form like this and just leave that as our final answer. So this question is a bit less straightforward than the previous one. If you look at this, if we were to do KCO for node 1 and node 2, there is this little source that will be giving us a lot of trouble. So what the source is going to do is make it so that we don't know what the currents going in these branches are. So what the answer key tells you to do is make a supernode. And that will work. And if you're wondering, a supernode is just us defining an arbitrary current over here and making all of these one node and solving like that, which me personally, I hate. I think there is a much simpler way of doing this, which I use in the exam, and it's like 2 steps. So what we're going to be doing is we're going to use the source to find the relationship between node 1 and 2, and then the other node we're going to be using is this node, or like the ground node all above, because KCL, it's the current law. It's supposed to work on any node. It doesn't just need to work on their definition of node 1 and node 2. So I can do whatever I want. So starting with the first step, we have, and I'm just going to name these V1 and V2. So we're going to have V1 minus V2 to be equal to 0.5 I3. And to find I3, all we need to do is refer to our circuit and see that I3 is just equal to V2 over R3. So putting these together, we're going to have V1 minus V2 equals 1 over 2 V2 over R3. And if we simplify this, we're going to have V1, let's see, minus V2 over 1 plus 1 over 2R3 equals 0. I'm pretty sure that math is right. You can probably run it yourself to double check. So right now, we are already halfway done with our question. We have one node equation. And if I was doing a super node, I would be playing with extra unknowns and extra equations and all that, which I am personally glad to not be dealing with. And for our other equation, we just use this bottom node. So it's just standard nodal analysis. I'm going to say currents going out are going to be negative, currents going in are going to be positive, and their sum, according to KCL, should equal to 0. So we have negative IS plus V1 over R1 plus V2 over R3 plus 2V1 equals 0. And rearranging this should give IS equals 2 plus 1 over R1 V1 plus V2 over R3. There you go. This is our second equation, and we are done with this question. We just solved it without having to do any of the special supernode, supermesh stuff that the answer key tells you to do. And if you ask me, this is a much more elegant solution.